Okay, so resonance is something that we really need to be on the lookout for. This kind of goes back to something we talked about in the previous chapter about electrons being waves as well as particles, or even more so, it being more appropriate to think of them as waves. That just results in conditions where the structure doesn't really match what we're trying to show, where we can't really indicate the electron as a dot. The electron is actually part of it's in two different places within the molecule, where we have bonds that are not 1, 2, or 3, single, double, or triple bonds. They're actually intermediate between single and double bonds, or between double and triple bonds. The only way for us to kind of correctly represent the bonding there is to draw multiple structures and realize that the actual structure we're thinking about is a combination of what we're seeing, right? Now, SCN, which would be thiocyanide, so thio means sulfur. This is like cyanide with a sulfur added on. This ion is another case where we'll see some resonance, although it's not the best one to start with. That's why I've kind of moved down to carbonate. But let's look at what's going on here, right? And this will give us a good example of kind of evaluating what the resonance means in terms of what the structure tells us about the molecule. So if we look at the structure, in terms of electronegativity, carbon and sulfur are both 2.5 in terms of electronegativity. So there might be a little question, should the sulfur go in the middle or should the carbon go in the middle? But if we think about formal charge, carbon we know is going to tend to make 4 bonds, sulfur is going to tend to make 2. That means carbon is a little better in the middle just based on how many bonds we can make. So this is actually written in the order of connectivity, but we probably could reason that if we didn't know that. So this is going to be sulfur, carbon, nitrogen. Now, count up the electrons. 6 plus 4 is 10, plus 5 is 15, plus 1 more for the charge is 16 electrons. Now, we used 4, 12 left. Right? Actually, that's kind of like CO2. That's enough to complete the octet around the end of the molecule. Right? Now from here, right, we may want to apply a little more thought to how we address some of these structures now that we know a little more about it. Looking at the atoms here, right, sulfur, column 6, the best structure for sulfur is 2 bonds. So sulfur is only 1 bond away from kind of reaching a drawing that would give it a 0 formal charge. But nitrogen is in the column with 5 valence electrons. It's 2 bonds away. So the first place to start to think about moving electrons might be there, right? And it might not be a bad idea when you're looking at these structures to make one move and then reevaluate. So if I make that move and make a double bond there, that gives me this situation. Okay, I'm still electron deficient on the carbon. I only had 4 electrons here. Now I've got 6, so I'm closer, but I still need 2 more electrons. But now there's more of an even situation here, kind of like we saw in the carbonate, right? 3 oxygens, one of them is going to donate the electrons to make a double bond. Here, the sulfur is 1 move away from getting to a 0 formal charge. But now the nitrogen is also 1 move away from getting to a 0 formal charge. So this represents a situation where we should be considering resonance. We should draw one structure where we share from the sulfur. We should draw another structure where we share from the nitrogen. So if we share from the nitrogen, we would get this picture. So the sulfur would stay with just 1 bond to the carbon, but we'd end up with a triple bond between the carbon and the nitrogen. 1 pair left on the nitrogen, 3 pair left on the sulfur. And if we shared from the sulfur, that one, we would end up with a double bond between sulfur and carbon, double bond between carbon and nitrogen. 2 lone pairs left on both the sulfur and the nitrogen. So the big difference here between these structures is going to be formal charge. The carbon is 0 in both. It's got 4 bonds, even though they're differently distributed. Over here on the left, sulfur has a 0 charge here, 6 minus 2 minus 4. But nitrogen is 5 minus 2 minus 4. That's where the negative charge resides. The -1 formal charge is on the nitrogen in the molecule on the left. Sulfur is where it is in the molecule on the right. 6 minus 1 minus 6 means a negative charge there on the sulfur. Carbon is neutral, 0 formal charge, and nitrogen also has a 0 formal charge here. So these are the two possible resonance structures of the molecule. And that means this ion has a structure that is intermediate between those two structures. Right? The sulfur-carbon bond, there's a double bond in one structure, a single bond in another. That's 3 bonds spread over 2 structures. That's an average of a bond and a half. So there's really a bond and a half between the sulfur and the carbon in thiocyanide. The nitrogen-carbon bond, it's a double bond in one structure, a triple in another. That's 5 spread over 2 structures. That's an average of 2.5. So there's 2.5 bonds between the carbon and the nitrogen in the actual structure of the ion. There's a negative charge on the nitrogen in one structure, negative charge on the sulfur in another structure. That means there's really half of a negative charge on the ends of the molecule in the real structure. It's half negative on the sulfur side, it's half negative on the nitrogen side. And again, if you think of an electron as a wave, that's perfectly reasonable, right? Not so if you think of it as a particle, but if you think of it as a wave, it is. So that's why we need to draw resonance. We need those two structures to really indicate what the bonding and the electron distribution actually is in the molecule. So keep that in mind. Look for those situations where you've got that choice. I can either do this, or this, or this, or maybe 4 different choices or 6 different choices of how to finish the structure, because we'll need to be on the lookout for that if we're going to account for the correct bonding information that we can derive from drawing a Lewis structure. Okay, so a couple more issues we need to tackle here before we've kind of covered everything we need to discuss. Phosphate ion here will give us another one. So phosphorus and oxygen, if we look at the electronegativity, phosphorus is 2.1. That's quite a bit less than oxygen. So phosphorus goes in the center, and we can connect oxygens to it. So we connect all 4 oxygens. That's all the atoms. So from there, we can think about the count of electrons. So phosphorus brings 5. 4 oxygens would be 4 times 6 would be 24. And then based on the charge here, the -3 charge means 3 extra electrons. So that's 27, 32 total electrons in the structure. Okay, now we used 2, 4, 6, 8 of them because we made 4 bonds. 32 minus 8 would be 24, right? And that's enough to put 6 on all the oxygens. So let's go ahead and do that. Finish the octet on all of the oxygens. Okay, and what we've said so far is now we would check the octet rule. Looks great. We've got 8 electrons everywhere, but we should also check formal charge, right? We want to satisfy the octet rule and minimize formal charge. If we look at formal charge here, right, every oxygen, 6 minus 1 minus 6, has a negative formal charge. So it's negative on all 4 oxygens. And then it's also going to be positive at the phosphorus. So phosphorus starts with 5 valence electrons. In this situation, it has 4 bonds. So that'd be 5 minus 4 minus 0, plus 1 on the phosphorus. Now, we want to minimize formal charge when we can, and here's where another issue comes up that we'll have to look out for in our structures. And in the handout of how to draw Lewis structures that you can get off Moodle that we've been talking about, down at the bottom there's a section on the handout called Other Things to Watch Out For. Right? And in the middle there's a topic called Expanded Octets. That means we're going past 8 electrons. This is something that will happen in a structure for larger atoms. So going back to our discussion of electron configuration, like right here, we're filling the 2p sublevel. Right here, we're filling the 3p sublevel. Right? The 3p is extended further away from the nucleus. So these are larger atoms than the ones where the electron shell is in the 2p. and they get larger as we go down. So it turns out these elements here in the 2p, carbon, nitrogen, oxygen, fluorine, 8 electrons is a hard ceiling. We cannot go past 8 electrons. There's just not enough space to put that many electrons packed that closely together around a smaller atom. But once we get down here, silicon, phosphorus, sulfur, chlorine, in the 3p level, these atoms are big enough that 10 electrons or more, 12, sometimes 14, could fit around one of the atoms and not be too close together to be unstable. So once we get down here, the 3p and lower, 4p, 5p, maybe even 6p, if we look at something like astatine, we can go past 8 electrons, and we will go past 8 electrons if it gives us better formal charges. And that means we need to start to be aware that we could have 5 bonds. Phosphorus and arsenic in particular can have 5 bonds. Sulfur, selenium, tellurium can go up to 6 bonds. And there's also some situations with sulfur, selenium, and tellurium where they can have 4 bonds and a non-bonding pair. Chlorine, bromine, iodine can go 3 bonds and 2 lone pairs, which would be 10 electrons. They can go 5 bonds and a lone pair, which would be 12 electrons. And they can even go 7 bonds, which would be 14 electrons. But all of those conditions could lead to a 0 formal charge. That means here, what we can do is share. So from one of the oxygens, we can share to the phosphorus. So let me just draw it from the top. That would leave all the other oxygens with a single bond, right? And then they would still each have 6 non-bonding electrons. What that would do is make this oxygen, where we made the double bond, have a 0 formal charge. It would make the phosphorus have a 0 formal charge, and it would leave the other 3 oxygens with negative charges. Now we need 3 negative charges because this is a 3- ion. So that would be a better representation of the bonding between the phosphorus and the oxygen in phosphate if we recognize that there is some double bond character involved in the phosphorus-oxygen bonds. Now, this would just be one of 4 resonance structures because we could do the double bonds in each of the other positions here as well. And that also means that the negative charges, right, 3 negative charges, they're actually spread over all 4 oxygens. This is less than a full negative charge on each of the oxygens if we factor in the expanded octet and all the resonance structures. That's the only way to get a true idea of what the real bonding looks like for phosphorus. So this video has gone on a little long. Let's come back. We'll do the other resonance structures to make sure we've got that clear in the next video, and then maybe we can wrap up the remaining pieces here as well.